I was just kidding. I was thinking about, hey, welcome back, by the way. Good to see you. I was thinking, what could I do to make it even more awkward? How about just long pauses? Is that awkward enough for you? Do you like awkward? If you like awkward, you've come to the right place. How's it going, everybody? Welcome back. Hello to you online. It's great to see you in person or virtually, either way. Should we start off with some announcements like I like to do? Okay, this helps. I am very forgetful. Either that or my life is too full and my brain is not big enough to handle it. So I write these down. I hope it helps. First thing, homework 2 is due tomorrow. You know that. Hooray. One thing about that homework came from intermediate statistics. Did you know the code that we ended with last week with that general version of Stan with the contrast and everything? That did everything that you did in intermediate statistics with that one piece of code. Did you know that? Isn't that cool? Think of how far you've come if you think of it that way. Everything you did in that class, be done with that one piece of code. Now it's all Bayes, but maybe that's better. I don't know. Anyway, homework 2 is due tomorrow. Yeah?
One of the instructions says that we have to describe the results, not only put numbers, but what kind of description?
That result section at the bottom
Yes.
is sufficient.
Okay.
Okay?
Okay.
Okay. The goal of the homework was to get you interacting with Stan, figuring out models, and understanding how to do Bayesian analyses. So in terms of interpretation, I'm less concerned as I am with just the execution of it, if that makes sense. Interpretation I'll be more concerned about as we get into the psychometrics next. Formative assessment 6 is online. I have some good news. There's no formative assessment next week. In its place, I might have a survey about how class is going, like a preemptive feedback, but that's optional. But encouraged to try to sign it. Depends on if I get it. Yeah.
What's the content for the assessment?
Formative assessment 6?
Yes.
I don't remember. I made it Monday. I've forgotten.
Okay.
Couple questions, huh?
What is the generated quantities?
Oh, there you go. Yeah.
Okay.
Why do?
And why do we want to yeah, that's right.
Yeah.
Generated quantities and why we use them in Bayes rather than just calculating.
Or why you would do those after sampling versus,
That's it.
Yep.
Thank you.
You're welcome. 1 hour of office hours today, 2 to 3 p.m. because we have a GMAS event that I'll try to go to after that. No class next week. Happy October. On Friday, our next assignment will be out. It's actually project part 1. So in place of a homework, you'll just have the project. Got 2 weeks to do that. There'll be an assignment that gets pushed from Icon. I didn't want to load up more than one while you had a homework outstanding. So homework is due Thursday. Friday morning, you'll get a notification, actually Friday midnight. Hey, there's a new assignment. That assignment will just be how to write up project part 1. We'll talk a little bit about it Friday. I will note that assignment in Icon, I took the list of ideas I've been forming for the project and put them on there. So you're welcome to have your own idea. At the very least, for the project, a data analysis. You have some data, you want to use Bayes, but something very vaguely psychometric will fit. Okay? But you can make it more complicated than that too. Sounds good? But the project part 1 is basically lay out what you want to do, why you want to do it, and begin the conversation of it. And you can also work in pairs. So up to 2 people per project. You don't have to. You can work individually. That will work as well too. And then, so I'll talk more about projects Friday. I wanted to show off, I know Nikki's been doing this. I don't know if anyone else has, but if you look at the pages section of Icon, this dictionary of terms page, thank you, Nikki, for your efforts about this, and for anybody who's updated it. Take a look. There's the dictionary of what we talk about in this class. So if you haven't seen that before, please take a look at it. It's very helpful. I think it's awesome. If you haven't contributed to it yet, please consider contributing to it while we're in class. It's really awesome to see. So I want to highlight that. I know, Nikki, thank you for your work on doing that. If anybody else has too, thank you. I don't get to see who modified it, so I can't tell. Okay? All right. Any questions for me? Nathan.
When we're reporting parameter estimates
Yes.
in articles, what is the APA format for
I don't think they have one.
They don't.
No. The format that you want to think of, the guiding principle you want to think about is what people would need to evaluate what your claims are. And so typically EAP, the point estimate mean of the posterior, some standard deviation talking about variability, and then that interval is important because a lot of times in APA format, you learn parameter and standard error.
Mm-hmm.
But if the standard error means less if the interval is not symmetric.
Yeah.
And so that's why the interval is important as well too. So I hope that helps. Yeah. But if APA has a format for it, I'd love to see it. But basically, show off as much as you can. Not show off, but describe what's happening as much as you can, providing evidence for it. Is the big thing. Other questions? Everybody seems kind of quiet today. Maybe I'm quiet. Maybe I'm projecting. I don't know. Let's see.
It's midterms almost.
Oh, anybody have midterms that I have to deal with? That's good. Not in this class. I don't know that Bayes lends itself well to tests, but I'd rather you work learning it than anything else. All right, well, let's dive in. I've got good news for you. I mentioned to start the class that syntax is the linear models. It's to the extent that intermediate statistics is all about linear models. There's more things than that in intermediate, I know. But the linear models portion of it, it runs all of it. Isn't that cool? Anyway, just thought I'd point that out to you. Bless you. Not only that, you've come so far. You know how to run an Markov chain. You know how to sort of troubleshoot if there's problems. You know how to specify your priors. You know how to look at the posterior distribution. It's cool, right? So this is the last steps in the Bayes part. So how do you know your model fits the data? And if you've got a set of models comparing and contrasting, how do you know which one you pick is better? And so those two features, those two questions, follow with us for everything we do, not just here in the simple linear model land, but this is especially true in psychometric models. A big part of what we do in psychometric models after we estimate a model is see whether the model fits the data. This is sort of the starting point for it. But what I'm showing you here for linear models will still apply as we get into psychometric models. They just get a little bit more complex. Okay? Are you excited? I don't know if words can express how excited I am for the end of the example. Because what I'm going to do, we're going to show how model fit works. Here, I'll just do this. We're going to talk about how well a model fits the data absolutely, something called posterior predictive model checks. And we're going to talk about methods for which model fits better, if you have multiple models that fit roughly well. So the end of this, though, at the example, I showed the example where I put the dumb prior in. Remember the dumb, I call it the dumb prior. The prior that really squished all the parameters versus the uninformed prior. We're going to try to get information as to what might fit the data better. I think we already know what that is. But then I throw it on its head and I'm like, hey, remember linear models, that assumption of homogeneity of variance? We're going to throw that on its head too in a Bayes sense, in a likelihood sense. And I want to make a point about that. So it culminates with that last part. Like, what's an assumption like that you have to have? And what's a modeling choice? Because when you look at the code for the last one, I'm actually going to we're going to take the variance of the model and model it too. So I want you to be thinking outside the box with that a little bit too. But that's last. And I learned in any good YouTube video, you got to talk about what's last first. Anything with a conference talk too, talk about what's last first, right? All right. Let's talk about PPMC, posterior predictive model checks. This is a way of talking about whether or not your data, or whether or not the model that you estimated fits your data well. So, hang on one second here. Yes, there we go. The absolute model fit question is this: does my model fit my data well? So what do we mean by that? Right? The result of our model, if we were to go and think of that as the truth, or our idea of what truth happens to be, our best guess as to what is happening to data, when we look at our model parameters and maybe we simulate data from them, that data that we were to generate from it, simulate from it, should look like the data that you collected. If it doesn't, it sort of implies the model is trying to do something different than what your data suggests is happening. And you may think to yourself, wait a minute, I'm fitting a model for a reason. How could that happen? And in the linear model sense, we're going to see it can happen with a bad choice of a prior. In a Bayesian sense, a bad choice of a prior can throw off what your model is saying with respect to your data. Now, in a non-Bayesian sense, we don't talk about model fitting, model checks in linear models, because there's really nothing to check that much. I guess there's the check that our variance is homogeneous, sort of a diagnostic, regression diagnostics. We also have checks for influence, but none of these, we never think about it in the same way that we think about it when we get to multivariate models, including psychometric models. Because oftentimes with one variable, there's not a lot to check, right? Did we recover the mean well? Did we recover the variance well? The end. When we have more than one variable, now we get more complications. Covariance, correlation, things like that. It's where multivariate models start to break down, is whether or not they model relationships between variables as well. But for a single univariate type of model, generally speaking, model fit is pretty good. Okay? Not always. It's just in Bayes, we have to worry about our priors, right? Our prior distributions, particularly when we don't have a lot of data, can put us into a spot that is not good. Actually, questions from online. I'm recording, yes. The project itself is blocked. It'll come out on Friday, so you'll be able to see that list of potential projects on Friday. So just sorry about that. Didn't see the chat before then. Okay. So what do we do in posterior predictive model checks? It's a little bit different than we see in frequentist statistics. So basically this, the ingredients we need are the original data, right? In our analysis model, this linear model example, what we're really after is not X, because we're not modeling X, right? Anything in the model matrix or the predictor matrix, we're not modeling. We're just taking it for granted. We need Y. So we have that. So typically, we often describe our original data with some type of statistics, some type of summary. Could be a mean. What's the mean of Y? What's the standard deviation of Y? We can go all the way up to any type of summary you're looking for. Then, what we're going to do with our Markov chain, remember the posterior distribution as we go MC, every step of the chain we may have new values for our parameters. We're going to take those new values, each of those values, take some sample of them, treat them as the truth, generate data according to our model, simulated data, and then take the same statistics on the simulated data that we took on the original data. And then, if you think about it, every time we do new simulated data, let's imagine we have the mean. We're taking the mean of Y. Right? We know what the mean is. We can observe it from our observed data. And we run our Markov chain. And every step of the chain, let's say, let's just do every one. We have a brand new set of parameters. We generate brand new data. And we take the mean of that new data, that new Y. So now, in addition to all of our parameters that we've been tracing throughout the chain, we may have a sample mean that we're tracing, right, from our generated data. That creates a distribution, something called the predictive distribution. And that predictive distribution, we say the model fits well if our observed value of the mean is somewhere in the middle of it. That's the big picture. So again, the same process of building distributions to characterize what we do, parameters or model fit, still carries forward with posterior predictive model checks. So I just gave you the whole process. we're going to walk through step by step, and then we're going to turn on Stan to make it work. I feel like I'm turning on the air conditioner, or I think we should refer to statistical programs in the old-fashioned sense, like especially if we could like work in what is the telephone that used to have the dial, like the.
A rotary.
There we go. I used to have one of those growing up. You dial up a stand program here. Anyway, going way back. That was way before like the whole like modem sound. Remember that? Anyway. All right, let's start with linear models. Any questions before I go on? That was the overview. That's like the 10,000-foot overview. There'll be specifics coming throughout. But do you have any questions before I jump in here? Now remember, why we do this? In a linear model sense, basically this is a check to see whether our priors have moved us away from the data happen to be. We're probably not going to get a lot of good information out of this with one outcome. It's in psychometric models that we start to see a big difference. Alternatively, any type of model that has multiple outcomes, a multivariate model itself, we'll start to see a big difference. But here is our linear model. We're predicting weight in pounds with height in inches, group 2, group 3, and the interaction between group and height. Right? Familiar with that? We have our estimates down here. We use the matrices to make that work. So this is the process of PPMC. We take parameters from a single iteration of the Markov chain. We're going to do this one at a time. Now, step 4 is to repeat steps 1 through 3 quite a few times. But you know at the end of our Markov chain, we have a lot of draws, right? The samples part of our stand object has all the draws in it. And it gets massive. Like by the end of this lecture, by the end of this week, our stand object will be about 300 megabytes, which is huge, right? It's going to have a lot of stuff in it. So let's take one single iteration drawn at random from that posterior distribution. Then grab our model parameters. So what are our model parameters? They are each of the betas and then our residual standard deviation sigma. Right? So we pretend that our model parameters are the true values. Right? So what does that mean? We want to come up with, and then we want to simulate a data set with this. What does that mean? For each observation of the data set, we come up with its expected mean by taking all the values of x and multiplying by the current parameters from that one iteration of the chain that we drew. Right? And we plug that in to this formula except for error, right? Up to group 3 right here. That's the conditional mean of an observation. The standard deviation for that comes from the sigma parameter. Right? So in this model, everybody has the same standard deviation. So what we do then is we calculate for each person, we generate a brand new y. What is a weight that comes from with a mean set by the betas, standard deviation set by sigma, and the distribution happens to be normal. We specified the distribution to be normal in our model for what y is, conditional on that mean value. So we use normal to generate it. You following me so far? Okay. So then, we have sample size 30, right? Remember, this is one iteration. Grab parameters, generate 30 new values at random. Right? Let's take its mean. Calculate its mean, or its standard deviation. And then save the mean or the standard deviation. That's the thought. So once again, then we do it again. Repeat steps 1 through 3 for a fixed number of iterations. And I put in parentheses here, perhaps across the whole chain. Because when we get Stan to do this for us, it's going to work on every one of the iterations. It doesn't have to be that way. Again, you can sample the sampled iterations if you really want to, which is like crazy to think about. But we do that again and again and again, building a number of observations that we have, sample means, sample standard deviations. And then when we're done, we make a comparison. We have this distribution of simulated sample means, for lack of a better term, again, a predictive distribution. We have where our observed mean happens to be. We put that in the middle. We try to see if it's in the middle of that distribution. So here's an example. Let's imagine we have one observed variable. Actually, no, we do have one observed variable, yp. And I'm also going to note that observations in x are not modeled. Right? Once again, we don't do that. So what am I talking about here? If I go to our stand model, I'm looking at this line right here. This is our linear model. We only have one observed variable that's on the left-hand side of the tilde, meaning we only have one observed variable in our model. Everything else is either a prior distribution or input into Stan without a distributional assumption at all, like x, right? So we ignore x, take that together, and let me go down here real quick. Nope. Go up here real quick. Evidently, I have put this in a different place. Well, that's fine. Let me just double check something. Yeah. Huh. Evidently, I made code and didn't save it. So I have it in my slides. Let's just look through my slides. Sorry about that. So you know this object, model 6 samples. We have draws right here. This draws function, and actually I can take this, and I can actually put this in my example right here. So model 6 samples draws is all of the variables themselves. What I do with this output right here is just to give us a matrix of draws. So I'm telling it, I only want beta and I only want sigma. And I want to put this into something called a draws matrix. And if I show you this, this is what I end up getting. I have each of our 6 betas plus sigma across the columns. And each row is one of the samples from one of our chains. Right, so remember, in this analysis, we ran 4 chains. Each chain had 2,000 samples after warm-up. So we have 8,000 total samples. We have all 8,000 listed in this matrix right here. Questions? Okay. So we take a draw at random. I'm showing you the process at random first, and then we'll throw it in Stan, okay? At random, I can grab a sample iteration. So what is this sample code doing? The sample function takes a draw at random from the set of numbers that you give it. So here I'm just telling it 1 through 8,000 is my sample. Pick one. And my sample iteration is sample iteration 3369 in my syntax here. With the random number seed online, I had 1103. But now if I want to show you what that iteration's value is, we can go in here. Those are the values of each of the parameters at that iteration. Still with me? Okay. So next, we need to take those values out of the format of this matrix and put that into something we can use where we have betas on one side and sigma on the other. So I loaded up something called a beta vector, because you know where I'm going with this. Once you start seeing the world with matrices, you don't stop, right? I see eye rolls. Really? Telling you. So one of my first classes I taught at Kansas, I'm going to tell you this story. How many of you had to memorize formulas in regression for regression slopes or regression intercepts? I told my students, I'll make you a deal. You have one formula for all of it, but it has to be matrices. They took that deal. I said, great. Anybody want to tell me what the matrix equation for least squares estimates of regression slopes is and intercepts?
It's prime and
Exactly. X transpose X inverse, X transpose Y. That is your linear model for least squares estimates. That's the one formula you need to know. You've estimated everything. The end. So they liked that trade. They liked it so much. Literally, I was leaving Kansas, moving to Georgia at that point. At the end, they made me like a cross stitch of that formula on a stuffed animal. I have that in my office, at my home office. So anyway, long story short, once you see the matrix, it's like that movie, The Matrix. Like once you see it, you can't unsee it, right? No, there is a spoon. Don't get me wrong, but anyway. So we're going to take the first 6 observations, put them in a beta vector. we're going to take the 7th observation and just put it in sigma itself. And sure enough, we're going to use, remember how we used the model matrix to tell us the conditional means for each of our, to input into Stan? We're going to use that model matrix one more time. See this model matrix that was from our model.matrix function. The conditional means is model matrix times the beta vector, or x beta as we're calling it in Stan. So for this draw, for this specific sample 33, whatever, these are the conditional means based on our model. This is not simulated, these are just means, right? We took the betas that were part of that draw, multiplied it by x, have the sample means. And we also know that the variance or the standard deviation for this is given by sigma. So now we can use a normal distribution to generate simulated data for that draw. Okay? So here's our sim data. We have n being our sample size, or 30. Conditional means is everybody's mean, and everybody has the same standard deviation. And now, whoops, these are our simulated values. Now you may think to yourself, why am I simulating data here? Why are we simulating data here? Why can't we just use the conditional means? Because those are model parameters. We want to express the uncertainty in the model with it as we go. And the full model itself has conditional means, or x beta for the means, but it also has another parameter, it has sigma. If we didn't simulate the data, there's no way we'd be able to assess whether sigma is functioning properly, because all we have is just conditional means, just fixed values at every part of the chain. Does that make sense?
Can you go back? You did like the 10,000-foot overview, and I don't think it quite.
Okay.
So I think I'm a little lost in terms of the exact steps we're doing.
Gotcha. We are taking a single draw, treating the parameters as known, and creating data as if our model were the truth.
As if that one draw was the truth.
That's right.
And so what you essentially did was create predicted,
The predicted, yeah, that's right. The predicted value is actually the conditional mean, the mean of the distribution of our model that we say for y. So we have to calculate the conditional mean to be our predicted value, but that actually turns out to be the mean in our data generation step right here. Okay, and then we have, so the conditional means are formed by a set of model parameters that are being sampled, that's the betas, and x, which we don't make any assumptions about.
And that's just like our observed data, right?
That is, yeah.
Okay.
Yeah, but our model is not for x.
Yep, yep.
It's all given x, that's right.
Yeah, we're trying to figure out.
Given means forgotten, that's right, yeah. We're looking at the outcomes, that's right. Forgotten, given and equals forgotten, maybe that's not entirely the case, but conditional upon these values of x, this is what we're saying y should be. Does that help?
I think so.
Okay. It's going to start to get a little bit more repetitive. We're going to see this over and over again, just like a Markov chain itself. A Markov chain is a metaphor for this class. Repeatedly, yes?
In terms of the word given, does that mean after controlling for?
No, it means conditional on.
Conditional on, okay.
That means basically I have no idea how x appeared, I just am using it.
Okay.
Yep. So if you think about it from a statistical sense, we have no idea how x appeared, we're just using it. Oh, and by the way, we're going to let it tell us what the mean of y is for each person.
Okay.
You
So
see how
it's
that's different?
like, yeah, that's like an external force that we don't want to identify versus.
It is, in other places we might call this exogenous to the model.
Okay.
Right? It is outside of what we're trying to do with our analysis itself. It may be important, but that's just, we're going to stay in our model's lane, which is just what the outcome variable for our model is. The flip of that, if you say, no, x is important, I want to model it, okay, well then we need a model statement for x or parts of x as well too. That would be where we would enter it in the model, and there may be cases later in class where we do that, but not for right now. Any other questions? Okay, so we have our simulated data. Next, we just need a mean of that. So the mean for our simulated data from this one iteration is 168.2644. And the mean, and actually I'll go, because we have all these data, we shouldn't waste it. Let's take the standard deviation too. The standard deviation is 50.40. Do you happen to remember what our data's mean was by any chance? 171 was our mean, and our standard deviation was 49. So you see, we're not too far off, but this is one draw from the posterior distribution. We don't run posterior distributions for one draw because the thing is going to have error to it. So we need to do this more than one time. Right? So we do this over and over again. I can't believe I deleted this part of the file that had all this. So I'm going to create an R object that just has empty values for the mean, an R object that has empty values for the standard deviation. And sure enough, I'm going to run through every single posterior sample, all 8,000 in the matrix, and calculate and save what the mean was and what the standard deviation is. So now, these are all our posterior means. These are all of our posterior standard deviations. Heck, we could plot them. There's our simulated means across 8,000 draws. Yes.
Okay, sorry, I just want to conceptualize.
No, this is good. This is a really, because we're sampling samples now, right?
It is absolutely the middle of the semester.
Yeah.
Okay, so we've got our 8,000 chains.
8,000 sample values from a posterior of our model parameters. That's right. Nope, I'm just going to be clear about what it is. Yep.
4 chains, 2,000 iterations.
That's right. So but we pool them all together because they converge. Yep.
From those, we essentially have estimates for our parameters.
Yes.
We have our betas, essentially.
That's right.
We are taking essentially one of those iterations, taking our model matrix, whatever, multiplying it to get our values, and then we're taking the average of those things.
Not quite. We are, let me walk you through it. We are collecting our parameters. That's this part right here. We're creating our conditional means. Based on our conditional means, we're generating simulated data. Remember we talked about what a model means? And the first part, a model is not just the parameters, but it's the distribution assumed as well. So here, we are generating from that assumed distribution. So we said,
whatever we get for the mean, we're plugging in as the mean of the normal distribution.
well, so model parameters, so the betas,
Yep.
from a single sample,
Yep.
we use that to give us the mean of all these normal distributions.
Yep.
And then we use that mean to generate data as if they were truly from that normal distribution. Does that make sense?
Yes, and then the standard deviation of that normal distribution is based off of.
It's a model parameter. It's sigma.
Okay, yes, sigma. Thank you.
That's it.
Thank you. Okay.
That's it, yes. I'm glad you're asking because this is, again, we did a simulation to get our posterior distribution, and now we're using our posterior distribution to do a simulation to see if it fits the data. So this is like a second level simulation.
And I've never done simulations, so I think that might be part of my.
No problem. We're going to get through it. Yes, and I'll be there.
Okay. So for example, in line 157,
Yes.
means equal that object model 06 underscore, that's the same.
That is what we call X. That's right.
Yeah, because those values won't change.
The matrix X, that's right. They're not changing at all. That's right. It's fixed. You're welcome. Yes.
So this is kind of the same thing we're doing margins in Lisa's classes.
Not quite.
Okay.
Not quite. So what we're doing, because we're trying to so remember the posterior distribution has all this variability in it, right? And what we're saying is, and not only is it not only variable, we've looked at posterior distributions one variable at a time. I have not plotted, although we could, a bivariate graph of a posterior of the two parameters. Like what's the posterior distribution of the intercept and one of the slopes, right? So what we're doing by taking a given draw from a chain, any correlation amongst the parameters will be reserved. So what we're doing is taking that and saying, okay, assuming this one draw were right, what's the data look like from it? Create the data from it with the simulation. Summarize the data, save it, right? So we're not marginalizing anything here. What we're saying is, let's assume the model is correct. Then every draw is a version of that correct model. So every draw I want to go and simulate based on what the model says to get a good sense of what the model says. So what I'm showing right here is the result of 8,000, all 8,000 draws, us generating 8,000 data sets of size 30. And then this is the summary. This is 8,000 means of those 8,030, n but equals 30 data sets. So what is it telling us? It says our model believes the mean for y to be in this range. So in that regard, it's marginal because it's just y by itself. But to get to that margin is a completely different process.
But this is just checking to make sure that everything is. So why not just trust, the sigma value that comes out of the.
Well, do you remember what happened when we fixed the tight prior, the highly informative priors the last time?
I wasn't here on Friday.
Oh, no problem. Let me tell you what happened.
Okay.
Our estimates for, so here in the slides, I have the original estimates here. These were our estimates. These are uninformative priors.
Okay.
When we put uninformative, meaning I think the standard deviation was 1,000 for each of these, if I'm not mistaken, or maybe it was 100. I don't know. Anyway, it was big.
A flat line.
Basically, when we put the standard deviation of 1, most of these values started to go towards 0. Like the intercept was like 0 point whatever. So they were way off of what the data thought they should be.
Oh.
And not only that, our variance then got really big. So what happens with the Bayesian model? There's several things that Bayesian model priors do that we don't want them to do. And what we're trying to do with this process is basically let them out themselves by saying, yeah, we're bad ideas, right? Because if we put a prior in, like you and I strongly believe these data should look one way, we could enforce that with the prior. And if we didn't do this, we wouldn't see that our belief might be wrong.
So this is double checking that the priors that we chose are good.
That's right.
Okay.
Priors that we chose, model that we chose. When we get to, the problem with this is it's a linear model. So I'm going to put quotes around it. It's simple, yet it's taken us how many weeks to get to the end? It's very complicated from a Bayes sense. But when we get to psychometric models, even if we have very uninformative priors that we find, the model itself may not fit the data well. It's a problem with psychometric models. We sort of create our reality, right? If you are assuming a unidimensional model and you don't have unidimensional data, for instance, that's a place where it doesn't fit well, right? So we need to see that too, and that's all wrapped together into this process. Did we pick bad? For the linear models, it's like, did I pick bad priors? That's basically all we can get when we have one outcome. That's almost all we can say.
And so I'm assuming the next step in this, we're going to compare the means from both and see how.
Yes.
Okay.
Yep. Well, actually, I'm just using this to see if we fit. I didn't go into that, but we could, certainly. Other questions? How are we doing? It's a lot, right? We're simulating stuff from values that we had actually simulated. Sure. You're down the MC rabbit hole. Why not, right? Okay. That's the loop across all the parameters. Here we go. I plotted. This is the plot of our distribution. Now, this is from the thing I did to run the slides. What I just did is a different random number generator seed, different values, but you can see the orange line is where our observed value of the mean is. The histogram are our sampled values of the mean, simulated values of the mean, the predictive distribution of the mean of y. And so what is this telling us? If we had a plot, by the way, that we wanted to see it fits well, this is it. The mean of y our model thinks the mean of y, the true mean of y comes out to be in the middle of the means of y that came from our model itself. That's what this is saying. The predictive distribution are the means that we're generating based if the model were true. We want this to happen, right? When a model fits the data, this is the data, it's saying, yeah, there's variability around it, but we would expect it. We only have a sample of 30, right? But this is appearing to give us what we want. The model is fitting the data for the mean. Same thing with standard deviation. That histogram are all the 8,000 simulated data sets standard deviations. The orange line is the observed standard deviation. There you have it. In the middle of the distribution, making us think our model is doing an okay job at thinking where the mean of the data are, where the standard deviation is. Now, as you get, I'm using this as trying to be a didactic example, meaning it's built for instruction. In general, when you have a model for an outcome that doesn't have any constraints across the parameters, like if you have like a psychometric model and you fix the discrimination to be equal across parameters, not that, right? Generally speaking, we fit each univariate outcome well with our models. It's a multivariate statistic that it shows model misfit as we go further. So here we don't have a lot of model misfit because it's very hard to misfit a model like this. So there are other ways. But anyway, big picture. How we do in understanding posterior predictive model checks? Yes?
Is there a way to include this in the stand syntax?
That's next. Yep. We're going to make Stan do the work for us. That's actually one of the better things about using Stan. If you go through my code from the last class, I have all this. I have a model which takes forever, and then I have a bunch of code afterwards trying to summarize it. To the extent possible, we will use Stan to do all this as part of the process. And the consequence for it will be it takes longer to write the code for it, and the output has more stuff in it. But otherwise, it works better.
And would you report this if you were writing?
Yes.
Okay.
What you want to say is my model fit the data. I use posterior predictive model checks to evaluate model data fit. I've got a couple more things about this that we'll say to describe it. Yes.
The simulation piece is still feeling like a black box to me a little
Okay.
bit. So once we get to the point of like, this is our normal distribution with the median and the standard deviation we figured out. What are we simulating? Like,
So let's think of it this way. Going up to our code here. Actually, let me go back here. This is the one example case. So our model says that y follows a normal distribution. The mean for every person's y is x times beta, and the variance is sigma. Okay? So a simulation would say, if you didn't observe y, but I had x, and I generated values for beta, and I generated values for sigma, then I can, at random, draw values from a normal distribution with those mean and standard deviation, and put those in y. So that's exactly what's happening with our model. We're basically saying, for our data, each observation, this is its mean. Right? Furthermore, each observation, this is its standard deviation. So what we do from there, the finishing step is to say, let's draw each of those from a normal distribution, where the mean for each observation is it changes, so there's 30 values. And the standard deviation is fixed at one value. Does that help?
we're essentially doing one draw from that?
One draw
Okay,
per iteration
yes,
of our Markov chain.
yeah. And those normal distributions are going to change a little bit.
The means are going to change, yeah.
Yes.
That's right. So think of it this way. So fix your eyes on here. Let's just take a look. 269, 4733 is the last value. If I draw a different sample, the last value is now 265. All right, so each iteration will have a different set of betas and sigma.
But simulation-wise, we're like only simulating one thing each.
Only simulating one data set each iteration.
Okay,
That's right.
cool.
Yep.
Thank you.
You're welcome. You're welcome. Yes. So you're inadvertently in this class, you're going to be understanding simulation, because simulation is how we check our model effectively. And it's sort of the idea. if our model were true, what does data it produced look like? And now it's like, all right, well, I've got this data. Does the data that my model produced look like the data that I just observed? If the answer is yes, it fits. If the answer is no, something's wrong. Yes?
And so if the model was perfect and everything, then the means from the simulated is equal the posterior.
No. If the model's perfect, by perfect you mean no error,
Yeah, like there's like
no variance?
When we compare the two, there's no difference.
That would be no difference, right? Yeah. The more precision we have in our model, actually, an image like this says the model is fitting well when it comes to standard deviation. An image like this says the model is fitting well when it comes to mean. Now, you might be a little bit dismayed that there's only an orange line here and a distribution there. However, and that's actually one of the things about PPMC, we're sort of doing a non-Bayesian estimate of a mean or a standard deviation and comparing with a crazy Bayesian process. One of your colleagues who's online here wrote a paper about this recently actually was published in Structural Equation Modeling about how we could do a PPMC process where it's different, but I want to teach you, this is the way it's currently done. I'd like to see the standard a little bit different. That other process, basically, you'd have to come up with a model for what the mean is. We could do that, and then overlay the two variations on top of each other. But that's for a different time. So, big picture of this process right here is checking whether our data and our model coincide. How are we doing? Any other questions? Boom. Okay, next. PPMC methods are very useful. They give you a quick visual way of determining whether a model fits the data. I would say that they are the main method used in Bayesian for assessing absolute fit of a model to data. Remember, absolute fit. That's saying, does this model fit this data set? Relative fit is which model fits better, A or B, right? It's possible to do relative fit. If you didn't check absolute fit, you could be checking between garbage models, right? Which trash is the best, right? I don't know. I live in Coralville. I like Coralville trash. Anyway, never mind. North Liberty trash is pretty good, though, too. Never mind. I don't know. Maybe you like Iowa City. It's fine. Point being, absolute fit is sort of the first standard you have to meet. If your model doesn't fit absolutely, don't even bother doing relative fit. Just sort of be like, yeah, that's not good, right? Comparing between my Coralville trash and North Liberty trash, what's that going to tell us, right? Doesn't do anything. Anyway, so that's good. But there's some clear drawbacks to PPMC. First, I pick the mean, I pick the standard deviation. You might say, you know what about the skewness, Templin? I'd really like to see skewness. We could have done that. We didn't. There's not a good set of rules, generally speaking, as to what statistics seem to make good model fit choices. There are trends in publishing that you see, and each of us who do this regularly for a living, we want to see sort of get used to when things sort of fit with something and doesn't fit with another, and for me, I wonder which one's better. But some statistics tend to be in favor than others. I can't tell you why or how. Second, there's no real easy standard to talk about how much misfit is too much, right? For instance, that's like right in the middle of the distribution. But if it were on the tail over here, we're eyeballing it. We're visually inspecting this. It's not precise enough for what we do. And then third, and this is the hard part, depending on your model, like if you have a psychometric model with 105 items, right? It can take a long time to compute this, right? To build, to do. So it is very difficult. It adds yet another complexity of Bayesian. Although people are trying to make it easier on you, that's where R packages proliferate. or if you get really good at coding things quickly if you're working in this area. Question online, can PPMC also be used for model comparison, relative fit-ish? Possibly, yeah. We do that, right? We say, oh, the PPMC on this model and the PPMC on that model, this one seems a little closer to that one. So we do that. So we can. It does. So the other thing about PPMC is the more complex your model gets, generally speaking. Again, if you don't put some really insane choices of priors in there. Remember, Bayesian, we can steer our model to work in ways that we want it to rather than the way the data do. But generally speaking, PPMC, the more complicated your model gets, the better it gets at representing your data. There's no penalty, generally speaking, in PPMC for model complexity. Right? So you make your model fit better, you add parameters. The problem with that is you start to potentially, depending on how you add parameters, you might weaken the arguments of generalization of your model, right? You may also, the relative impact or relative increase in model fit for a given parameter or other terms may not be easily quantifiable. So this is why relative fit measures and relative fit indices are built, because PPMC is important up to a point. But then if you've over-parameterized your model, if you have too many things in it, it won't tell you that. So that's sort of the drawback of it. So if all we have with PPMC, we'd sort of lean on the side of overcomplicated models that may not generalize well because we may have had to add more things to the model to make it fit. Does that make sense? Hopefully that answers your question on that. Okay. Now, there is a flip of PPMC that we do start to use a little more, something called the posterior predictive p-value. Oh my God, a Bayesian p-value, sort of. And I put p-value in quotes because it's not the same as the p-value you're used to in frequentist statistics. All right? A posterior predictive p-value takes a look at this plot and figures out the percentile at which the observed data falls on the distribution. Now, percentiles can be calculated from if you order your data from lowest to highest or highest to lowest, right? Either way, it's a percentile. And either way, it will tell you if you're an outlier. If your observed quantities are in the tail of this predictive distribution. So the posterior predictive p-value is more like a PPMC percentile, but there's already too many letter P in that acronym, so I don't know. Anyway, what do we do? What can we do? We can basically take the count or the proportion of which observations in that distribution were bigger than our sample mean, right? So this is the PPP value, or posterior predictive p-value for the mean. It says 44.9% of our sample values, our simulated values, were bigger than our sample mean. Now, if that didn't fit, we would see that p-value number would be like 0.99, right? Meaning it would be in the lower tail, or 0.01, meaning it would be in the upper tail, or something along those lines. But what the posterior predictive p-value does is it turns this plot that's a visual inspection into something numeric by which you can quickly sort data to determine where outliers or otherwise model misfit occurs. Yes?
To compute that thing, are we using a specific number of the observed family statistic, or can you use some kind of interval? Because, for example, if the number, if the observed value is 9, and my simulated number is 9.01, that's larger, right?
Yes, yes. This doesn't say how much larger.
Okay.
This tells us just if an observation is larger or not. So it's giving effectively the percentile rank of the observed mean against the posterior predictive distribution that we formed for it. Now you could, there's another thing, anything, so that's the nice thing about these distributions. Anything you do to summarize them can be valid, right? So another thing you can talk about is, how far off each on average, how far off is your simulated mean from your real mean. You could do other statistics if you wanted to. But the p-value is what we've sort of landed on right now. Yeah.
I don't know if this makes any sense at all, but
Mhm.
KL divergence, could you use that to see how far off?
So if you remind me, Zhihong has a paper that he did just that.
Okay.
But we did a posterior predictive distribution where we fit two models, a null model and our expected model.
Mhm.
And so we have two posterior distributions, or two predictive distributions. And then we sort of use a KL divergence, or, well, KL is one of it. We use actually KS, Kolmogorov-Smirnov, as a statistic. But there's, again, it's no longer some weird statistic you've never heard of. It's how do I compare two masses
Yeah.
and see to define discrepancy. That's basically what it comes down to. And the sort of the power of Bayes is that, you can think like KL would work, or I could think KS, or Latimer, you can talk about magnitude or mean absolute deviation or something along those lines. And none of us are really wrong. We're all describing this picture with slightly different quantitative methods.
It's just weird because now we don't have assumptions that we have to deal with, and so or things like, oh, you shouldn't be doing this. It's just whatever, because we have everything there.
That's right. It's right.
So,
It's right. Like literally you have all the result. I mean, there still are assumptions on the back end, and you can still find ways to cheat and lie with data if you really wanted to. However, the concept of what I'm trying to form from the conceptual point of view is once you have all this, literally it becomes a problem of a basic statistics problem. Getting to this part is not basic. Think of all we've gone through to get to this part, right? But once we have it, now it's summarizing a distribution versus a value, or summarizing two distributions. Which, ironically, is like back to the basics, right? Okay. So let's do this in Stan. And wouldn't you know, generated quantities is where we could make this work. I gotta tell you, generated quantities is why I'm like, all right, Stan, not too bad. So what do I mean by that? Turns out there's a function that you can use in Stan that can generate normal data. It's right here, normal underscore RNG. Random number generator is what RNG stands for, okay? It relies upon the two parts that we're used to having, a series of predicted values, or conditional means, and a standard deviation. So what we will do in Stan, remember what happens in generated quantities, is after sampling for an iteration is done, all this code runs, and it saves the results, if you didn't put an inner set of curly brackets in, right? So, what Stan will do is by this command, it will create a sample of 30 observations generated randomly from the values that we tell it for the mean and standard deviation for it. And those 30 observations will continue across the entire chain. So that means for all 30 of our observations, unless we tell it not to save it, we're going to have a predictive distribution, not just of all 30. We're going to have each person. Each person in our sample will be able to see if they fit well as well. So let's think about how we build that. First, we need the predicted values. So I, at the beginning of the Stan code, created this vector to create y predicted. This looks like our data, right? And when we input data into Stan, we use vector n y. In generated quantities, I'm doing vector n y pred. And then I set y pred equal to x beta, x times beta. Remember, that's the matrix product. Because in Stan, x is a matrix that we're inputting. Beta is a vector. And as the dimensions line up, it will make the product for us. So that gives us a 30 by 1 vector of predicted values, which will be our conditional means. So then, to save our generated values, our simulated values, I create another vector, or call it an array in this case. Yes?
Okay. So here in line 5, that beta, it is the thing that will change at the end of each something.
That's right. It is what we define in parameters here as our parameters and that we submitted to our model for y itself.
And that will be stored and then upload that.
That's exactly right. Yep. So that's the nice thing. Generated quantities lets us take any of the parameters or any of the data that we've submitted to Stan and to use it in calculation. So here, we save it. That's all 30. And so this other syntax that you see below it is our summary of that step. So we might want the mean of y, the standard deviation. So these first two terms are sort of not all that helpful. These are just the actual observed mean of y and standard deviation of y. Those are not going to change from step to step in the chain. They're always the same because y is not changing, right? Yeah.
So if you visualize like MCMC density, then those will just be okay.
Zero standard deviation, like, and if you try to build an R hat off of it, it will give you an NA value because R hat is a variance. And we're taking a ratio of variances. So one of those variances is on the bottom, and anything divided by 0 is not defined. So we get NA, not a number for it. Then we may want the mean of our simulated values. That's what this does right here. We may want the standard deviation of our simulated values. That's what this does right here. And these other two values are for posterior predicted p-values. Basically, we're going to count up, we're creating an indicator variable, an integer that can either be 0 or 1. And it's going to say mean greater than or equal to what we currently have. That's the mean of our simulated data for that sample, for that one sample, is a 1 if it's greater than or equal to our sample mean itself, overall from our data. And the same thing with the standard deviation.
So you don't have to do if else, you can just write that.
Not in this, yeah. And so when we actually output it now, this is what we get. These are the outputs. So what is this telling us in it? Remember, in the samples object, it contains all sorts of information from our Markov chain and our generated quantities, right? So in your homework, you have R squared there, hopefully, right? Or you have some linear combination, the contrasts of your parameters sometimes show up there. We're using this now for posterior predictive model checks. And in a moment, we'll use it for absolute fit as well, or relative fit as well, too. Or I guess that moment might be Friday. But what we see here is this mean value. This is the chain summary of our simulated mean across all of the draws of the chain. So the mean of it is 171. That means that if what these summary statistics are telling us, this is our distribution of the mean that we created ourselves. Stan has its version of this. It's telling you where the mean of this distribution is, the predicted distribution. And then these are the other quantities in that predicted distribution. Heck, it even tells us whether that converged. All right, which is not guaranteed to. It should, though, if all of our sample is converged. Standard deviation, same thing here. And then these last two terms, this is the posterior predicted p-value. It said 0.441. That says 44.1% of our observations, our sampled means, were greater than or equal to the observed mean. What do you think? Are you overwhelmed? Posterior predictive overwhelm statistics, PPOS. No? Never mind. POS, by the way, never mind. Let's think of other terms that POS stands for. My first job was in food service. That was point of sale. That was our cash register. I drove a POS to my first job. It was an El Camino. That was my first car. 1977 El Camino. Anyway, now, you're too young to know what an El Camino is, but they have not brought that one back, and it's probably for a reason.
Is that the, like, car truck?
The TRAR.
Yeah. It was in some song my brother really listened to.
See if I can get a picture of us here. This is it. This is like what I used to drive. Well, it wasn't in that condition. It had rust on the hood. I was lucky because it was about to fall apart and my parents let me use it my 16th birthday. But yeah, I was driving that POS car, piece of something car, to use the POS machine before I did PPOS for, never mind. Okay, too much. But I got my El Camino reference in. You know, like everything old is new again with cars, like we've got the Bronco is back, which actually is kind of a sweet looking car, I feel like, right? When they bring this back, you know the apocalypse is near. That or the Ford Pinto, right? All right, never mind. I used to like cars. Okay, yes?
Just because I'm curious about this, could you put like the formula for the KL divergence or KS divergence in the generated and then?
Yeah, and actually in Stan, there's another block of code where you can define your own function.
Oh.
So you can define your own function and then put it there and then call that function in it too.
Does that use our language or does
It's the Stan language, the conventions, but yeah.
And what is 2 underscore vector?
So this is an array because of the result. The result of the random number generator wants it to be that way, which means it's not, but the mean function needs a vector. So the 2 vector is just a thing that takes an array and makes it into a vector to evaluate. It's kind of like an R, if you have a matrix, it's not a data frame. There's the as.data frame function.
Yeah.
Converts, it's a type conversion is what we call that.
Okay.
All right, other questions? How are we doing? Is this fun?
So we basically are doing hypothesis testing, but we're making everything.
Well, so the hypothesis testing is different.
Well, I'm saying like
Yeah.
if you're like, you know, mean 1 equals mean 2, we're actually, instead of predicting or whatever, we're doing it.
Right, exactly. We're going to build our own posterior of everything that we can, for the most part. Why I say hypothesis testing is different is there sort of a frequentist Bayesian debate about what a null hypothesis is. Is it the likelihood of the data conditional on the hypothesis, or the likelihood of the hypothesis conditional on the data? One is one is the other. And in Bayesian, then we'd need a prior probability of the null hypothesis, which we wouldn't have as well. So there is a whole segment of Bayesian hypothesis testing that we're not going to get into. So this, if we were testing any hypothesis here, and it's barely even that, but I guess the hypothesis would be that our model fits the data is our null hypothesis, and the p-value is trying to test that, posterior predictive p-value. But it's a 2-tailed p-value, so it's weird, right? So it's a percentile. Okay. Want to try? So, other questions on absolute model fit? Okay. Do you have seat belts in your chairs? Because things are about to get rocky. I just warn you. But I promise the urge to put the integral in my slides was strong, and I didn't. So just for reference to what that is referred to. Like the technical documentation of model fit, even posterior predictive model checks, is very technical. But
Will you tell us where you were going to put the integral?
maybe.
Calculus helps me, that's why I'm asking.
I'll help you. I'll help you. Here, I have a link right here. There's a link to a paper on arXiv. I put the arXiv. It's a preprint, but it's been published, but you can still access the preprint. But basically, there we go. Tell me when your eyes start to glaze over. How are we doing? Oh, not as integrals, by the way. Let's not forget about our Taylor series expansion. Okay, so I say it's somewhat technical, or very technical. So I'm trying to minimize that because I think to use it, so long as other people have vetted the technical part of it, we're okay to use it, right? In other courses and other disciplines, we would study the technical aspect. For us, we're going to use it to our benefit.
Sometimes I think like I'm on the same page because if I see the like formula, sometimes translating it into words helps me.
Oh, I understand.
Relate.
And normally I'm all for the formula.
Yeah.
For
But
this
now
though,
it's just a lot.
we're talking like simulation with a formula, and it's a lot. Yeah, we're going to be. Yeah, I decided it's not good. It's like auxiliary material. I put a link there. If you want more references, it's there. But it's tough. All right, let's talk relative model fit. I'll start this here. We'll continue Friday, but I do encourage you to try to attend or at least watch the video on Friday because the cliffhanger. Do we have heterogeneous variance is the question. We're going to answer it. Okay? But let's talk relative model fit. We want to use this to compare two models. Remember, a prerequisite to that is those two models should have some type of semblance to the real data. So in theory, if you have model A and model B, you should be PPMCing those things to figure out that they fit. I just use PPMC as a verb. All right, you know what I'm saying? Both of them should fit the data well. Okay, if you weren't in Bayes, you might think of something called information criteria. Have you ever heard of those before? AIC, Ake information criteria. BIC, Schwartz's information criterion. The B actually stands for Bayesian information criterion. Ironically, we're not using that in our Bayes class. Okay? Bayesian model fit's very similar. We're going to use some index of information criteria. And we're going to pick the model that has the lowest value of that index itself. Now, giving you a 30-year summary in like 2 minutes. Once upon a time, before I was even in grad school, people were doing Bayes with something called windbugs. Spiegelhalter, David Spiegelhalter, I think is the name of the person who created them. World-renowned scientist, actually writes for publications in England right now, and I can't remember which, The Guardian or something like that. Anyway, he writes, he's well-known. Came up with something called the deviance information criteria, which was used with problems, and people were studying it. And as in the last 10 to 15 years, things have really gotten better about model fit in Bayes. So most recently is the linking between Bayesian model fit indices and cross-validation methods. Now, cross-validation methods, what are those? Think of it this way. We have 30 observations in our sample. If we really want to do cross-validation, what we could do is run 30, choose, I don't know, I guess 30 different models, leaving one observation out at a time and making predictions on that observation. And then quantifying how far off our prediction is for that. That's a cross-validation approach. Turns out there's a link between these indices of model fit and cross-validation. As you know, we're already doing computationally intensive stuff. So to do 30 different models, or however many different models, to do cross-validation is infeasible, right? So instead, people have come up with indices that try to mirror what those cross-validation results are based on some educated guesses as to sort of tendencies in the data, tendencies in the models, and so forth. The impact of all this that you need to know is that we may start using something called a leave one out index, but not do a leave one out process to get to it. That's where we're building toward. Okay? So you'll see the term leave one out, meaning leave one observation out from a cross-validation standpoint. And this index that we're building does not do that directly, but it tries to approximate it in practice. Okay, this is the deviance information criterion. Basically, it is a penalty of the number of parameters your model has, which is estimated based on an average model fit likelihood based on your model. So that's what this D bar is. Deviance information criterion still gets used, still gets published, but I think you're going to see some of the citations we're using. We're talking like 2018, 2019. Things that are very recent scientifically have, I think, moved model fit into a better spot. They're just somewhat difficult to understand. So DIC has a problem. It's not fully Bayesian. If you have discrete parameters in your model, which we don't, but if you did, we don't know really how to do it. It can give negative values for estimated models, number of model parameters. That's bad. I'm going to stop here. Pretty soon, we're going to talk about something called WAIC. We'll start Friday there. But I'm out of time for today, and I hate running late. So thank you for your attention. I'm telling you, Friday's a cliffhanger. Do we have heterogeneous variance in our model is what we're going to answer. All right. See you Friday. Thank you for being here. Thank you to everybody online.